Hello again, welcome. This is Robert Felt, and this is the second installment in this little series where we use different automated testing techniques and ideas on this little min-max filter. So we have this min-max filter, and if you want to know more about that, that's the SUT, the software we're testing, software under test. You can go to the first part of this series where we introduce the problem, which is a filter, and it keeps track of the smallest and the largest value seen so far, and we can run the filter over many different sequences, lists, or vectors of numbers, and it will keep this state. Remember the min and max. And in the first part, we used bounded exhaustive testing, which is nice and quite simple to get going. And in this one, we'll be using random testing, which is another simple thing to use, which can also be quite effective. So random testing, what's the motivation? Well, one good thing about it is that when we don't know, we don't even have a hunch of what type of bugs are we looking for, then it can often be quite effective to use random testing, because we don't really bias a random test generator. We write it in a very short and succinct way, which is also a benefit because there's not a lot of code. We don't need to keep a lot of state. We don't need to remember in our generator where we have been before. So we take random decisions when we generate a piece of data, or even the steps in a whole test case we can generate in this way. So it can be easy to write, short, and thus it can also execute very quickly. But some downsides can be that if the bugs you're trying to find need very specific inputs, you might be unlikely to hit them, to generate them with a random test generator. So it's kind of like a flip side here. It's good because it's hard for you to build in biases in your random tester. So this can be just good because you're not limiting it to finding certain bugs that you have a hunch about, so you can find other stuff. But it also means that it can be difficult to find things that are where you need a very specific input. And there are other downsides. So the data you generate will not look like normal inputs often. So it can be a little bit harder to find actual bugs if the bugs are sort of happening closer to realistic normal inputs. But maybe even more of a problem is that even if you do find bugs with random testing, they can be a little bit more difficult to analyze and understand because your data doesn't look very normal. So it's a little bit hard to see what's going on in your data. So what are the steps? Well, in some sense, you still need to think about bounding your space, because just randomly generating any type of allowed input can often be difficult. But, at least you need to give some thinking here. But the space here can be, very large. It can be based almost on the types that are allowed, or typical types that will be used, and so on. So in some sense, you don't need as much information to bound the space for random testing. And it can basically be based on types and how you put together random data sampled for each of the types involved, and so on. And once you have this space, well, then it's basically just to sample from it, right? So how do you do this in this little language we're using here? I mean, of course, any language will have this. In Julia, I'm using here, it's called rand, and this is a function. And when you apply it to the type, for example, int here, and if we execute this, you can see here that every time I execute it, we get a different random integer. But you can also see that they tend to be really large. So this is typically not how integers look in normal inputs to software systems. Right, so you can also provide a range. So in Julia, you can have the same function name overloaded depending on the argument types. So here we're, instead of giving a type, we give an interval from the integer 1 to the integer 4. And applying rand function on that, or method, means that sample one of these values that I provided. So if we run this again, you see that we get different values from this range, right? So also very useful. So then we know how to randomly generate both the length of an input vector, so we can use this construct here, and the values if we want to put, say, up to 4 values into an integer vector. We can first get the length, and then we can apply call rand int for every element we need to generate, and just add them to a vector, and off we go. You know, to be a little bit more fancy here and show you some of the type of things you typically do in random testing, is you want to go from the full space to something a little bit more realistic. So often then you use random sampling several times. So this is the typical way. So let's say we want to maybe not have these 64-bit integers, which is the default in Julia when you're running on a 64-bit machine like I am. It can be 32 bits if you're on an older machine, or it can probably be 128 bits in the future. But anyway, Julia has many integer types. So there's int 8, which is an 8-bit integer, int 16, 32, and so forth. So yeah, so instead of using int here, we could go like int 8, and then we get smaller integers here, right? We can go up to 16 bits, of course, and then we tend to get a little bit larger. There's also like types for unsigned integers, so they are like this, and then you will never get a negative value. It's actually represented in a different way, just to make a difference here. But you know, we can go down to 8, and then we get values between 0 and 255, I guess. And so on. But you know, let's for the example there we can use int. But down here, let's say that we want to use first we flip a coin. So we apply rand on the float here, and we check if you know, this rand float will give us a floating point value between 0 and 1, and we can use this then to sample a probability in a sense. So let's do a generator of integers that with 80% chance gives you an 8-bit integer, and with the rest 20% chance give you 16-bit. Well, you know, here's a function called myRandInt. It takes this the rate here with which I will sample an 8-bit integer, and then it has this statement here, which is check this first, which is take a random value between 0 and 1. If it's below 0.8, the rate here, then we return the first part. If it's not, so if it's between 0.80 and 1.0, then we take this part. So basically, yeah, flip a coin here, and with 80% chance return an 8-bit integer, and with 20% chance return a 16-bit integer. So yeah, and then we can now create an int vector by doing this a random number of times, and the number of times is between 0 and 6. Then we call this function every time, and you know, then sometimes we get length 0, then we don't call this at all, so we return an empty list or vector. And if we do this again and again, then you know, we'll get different random integer vectors here. So you know, this is just showing you the type of thinking that typically goes into random testing, that you can adapt a little bit, doing one-liners like this to make it a little bit more realistic. You can, you know, there are of course libraries that help you do this in a more flexible and general way, but for many languages, if there is no such library, as long as you have the basic building block of generating a pseudo-random number, you can build this up, this type of testing quite easily. Okay, so let's just put this together. So let's do a function so that we can generate several of these vectors, so we can use them all for testing. And I just generalized this a bit. So this is basically the function from above, but we can say that we can give the minimum length that we allow, the maximum length, and the rate here. And then this function gives us one vector. And then in this function, we then apply this first function several times, and we can state how many of these we want. So now we have a generator, and we can say, give me 10, or we can start with 3 vectors where the maximum length of each vector is 4, for example. And if we run this, here we get 3 vectors, and they have a length of 3, length of 2, length of 1. And we can play with this. So say we want to run 6 tests, then we can change it. So you see here that this is a typical random testing generator. And of course you can adapt the types that you generate to what you need for your type of testing here. Okay, so let's use this now generator in the same way as we used for the bounded exhaustive testing. We create a filter. We actually on top here, we generate 100 vectors like this. And we say max length 3, and we actually put the min length at 1, because we already know that for this soot, having a 0 here gives errors. So we can try that actually. Yeah, we get 44 errors here, and 111 pass, 45 fail. So to skip the errors, we go with min length 1. And we still get a lot of failures here. Even for only 100 generated inputs here, we can go with 10. We still get some failures here. So this is a bug or a problem that is quite easy to find. In the same way, we can look at the errors. Now with min length 1, there are no errors. So, okay, we can do the same trick of kind of looking into these failures instead. We had 65 failures here. We can take their length, and we can save in a variable data length here, the unique lengths that we get. We get something from 3 is the minimum up to 18, it seems. And then we can filter on the minimum. So actually show us the failures for the shortest inputs. And yeah, there's apparently only 1 here if we look at them. And this is for the value 5. So what if we rerun this? We take some larger number. And yeah, now we get more of them. So you can see here we can do the same type of exploration as we did for bounded exhaustive testing. But of course I will not repeat this again. Okay, so the good thing is that if for bugs like this that are quite that happens for many of the inputs, it's quite easy to find them in this way. But if you then have a hunch and you need some specific type of input, how would you use random testing? Well, there are 2 main ideas, and the simplest one is called generate and filter. I mean, it's also known as generate and test, but I try to stay away from the generate test term because it means testing the inputs or the data that you generate, not testing the soot that we're trying to test ultimately. So I will call this generate and filter, but you will hear people also say generate and test. The basic idea is this: just you write a random input generator like we did above, and then you check, does this specific data fulfill my criteria? If not, generate a new one. So we're basically just filtering the randomly generated inputs or data and only keeping the ones that we want to look at. So we only return the inputs that fulfill our criteria, right? So let's say that we have a hunch that, okay, I'm not interested in these failures that happen for only an input of length 1. I need to look at something more specific, and maybe like in a similar way to what we did for bounded exhaustive testing, we have a hunch that the length, if the length is 2 and the first element of the 2 is larger than the second element, then that seems to be a problem. So let's say we want to generate this in a random generator. What we would do is write down our criteria. So the criteria is length should be 2 and they should be descending. So the first one should be larger than the second one. So then they are descending in size. So we take some vector as input to this criteria function, and we define our criteria function as first checking the length. So the length of the vector should be 2, because this was our criteria. And it should also fulfill that the first element of the vector should be larger than the second one, okay? And then we just use the generate and filter approach. So we write a function, generate and filter a random int vector with our criterion function. So this is argument here is the criterion function. We can put in this, but we can also put in other criterion. And, you know, until we find a vector that fulfills the criteria, we will loop and generate a new one. So here we are actually reusing our random generator, which was give us a random integer vector. And here we actually can tell this generator to give us length 2 by setting minimum length to 2 and the maximum length to 2. And here we're using the 80% again. But, you know, you can easily generalize this to much more complex criteria. And then you would generate, filter. Okay, so the first time we fulfill our criterion, we will return, and we have generated one input or datum. So if we use this, then we see that, okay, length is 2, and the first one is larger than the second one. And we can repeat this, and all the time it's the same. Even when they are both negative, then okay, minus 34 is larger than minus 43. Okay, so let's use it again. So we rewrite this. So we say that loop 100 times, and in each time we generate the value, which is our test input, by calling the generate and filter function with this criteria that we have, that we wanted to look at. We have a hunch this will be important. The test code and saving of values is the same, and you know, we can rerun this and we get again 100 failures now, 100 passed. So this means that when now we have verified our hunch that when this criteria is fulfilled, one of these will always fail. Let's look at which one is it. Okay, so it's the largest. Okay, so this line will pass for all 100 iterations, and this line, the largest line here, will fail for every. And if we look at these failures again, so we sort them based on their length. The length is the shortest length now is 7, and then we see that, okay, here are some examples for when this happens. Of course, they are random now, right? So they are not exhaustive in some space and so on. It's just a few samples. So, you know, it could happen that some of them are the same here, but we don't really look for that. Okay, so it seems clear that if the values are in descending order, there is a problem. But to be sure, let's just write the different criteria. So we change the criteria and we say the length is 2, again, same way, but now they are ascending. So the second element is larger than the first, okay? So now we have defined this down here. So it's defined here for Julia. So now we can copy this and go up to our test code and we put it in here. So we had With descending values, we got 100, 100, and if we have ascending values, oh, we get all tests, 200 of them passed. So we go through this 100 times, and there are 2 tests in here, so all of them pass. So now we have gotten a lot closer to understanding this bug, and of course, I mean, we can go further. So maybe we check, make this into a 3, or maybe we make it. We take the length here as a parameter, and we look for that length. Oh, that's harder, right? Let's skip that. We go for length 3, and we do length 3, and now we should have, let's do descending now. So we should have that 1 is larger than 2, and 2 is larger than 3, right? And we check first that the length is 3, so this should be fine. And now we can use this criterion up here. Okay, we get an error. Where is... Oh, it's taking a long time. What is happening? What did I do? Ah, yes, this is great. This is showing the problem here. So this is one of the problems with this approach. Perfect. If we only want to generate 2 of those, that should be faster, I guess. Ah, no. Of course, we are only, in our generator here, we're only generating vectors of length 2 here. Right, so we need to generalize also this code, but for now let's just put a 3 here, and now we can have 2 here. Let's go for 100. Okay, so if the length is 2 or 3, now we know that, and they are descending, then we get the same problem. And you can play with this like this, so you can generalize your generator and filter and criteria to investigate different ideas you have. So this can help full in testing and debugging to understand what's going on. And okay, so this was the general and filter method. But another way you can do this is the custom generator method, which instead writes the random test data generator, so it will always create the data that fulfills your criterion, right? So let's say again that we want to write now a custom random descending vector. So the values should be in descending order from the largest to smaller. And we want to give a specific length here. How can we do that? Well, we use our randint vector. We generate something of min length len and max length len with 80% chance of having a small integer in them. And then we just sort this. And in Julia, a sort function by default will go from in ascending order, so from the smallest to the largest. So we reverse this. So this is a parameter to this Julia function. So if we define this one and we apply that to the length 2, we will get something where the first element is always larger. So this is a big, if we change to 4, we get 4 of them like this. So this is much more efficient than generate and filter, because we only generate one vector and then we just kind of change it to fulfill our criteria. So this requires more custom code in a sense. You need to write this in order, and sometimes it can be hard to fulfill the criteria you want to fulfill. But the benefit is that it's faster. So that's another way of doing it. So generate and filter, often simpler, you can switch out your criteria quickly and so on. But doing a custom generator like this, you can be, you can really adapt to the stuff you want. And this is actually used in the third and last part of random testing here, that I will talk about, which is randomly generating a more complex data. Well, what you do is basically you use this idea of writing custom code, a custom generator. So let's say that you want to generate some kind of dictionary, so a map from keys to values, and you want the keys to be strings, and they need to be at least 3 characters long, and they should and those are the keys, and each key maps to a vector of numbers or strings, and those vectors must have a length of at least 2 elements, but they can be up to 5 elements. And then the numbers that are in there can be either small integers between 0 and 100, or small positive integers, or floating point numbers in the same range. So, what do we need from Julia to do this? Well, for your language it will be different, but let's say there's a rand string function in Julia base. So you can use first randomly sample an integer between 2 and 5, and then this is the length of a random string. So if we run this, we get different random strings here. And of course you can specify which characters are allowed in your strings and whatnot. And then we can use this to write now a custom piece of code where we say how many maximum number of entries in our dictionary, the maximum string length for the keys and for the strings in our vectors, the resolution of our floating point, this is just how many decimals do we want on our floating point numbers. And then we write a custom piece of code to generate the data that we need. And so it's quite simple. Okay, here you have a few lines of code, but basically create an empty dictionary of a certain type. We don't need to go into this. Then, for between 1 and, between 0 and maximum entries of 10, select a random number between 0 and 10, and then generate, add a key and a value for each time you loop here, and update the dictionary, and then return this. And how do you then generate the value? Well, it was supposed to be a vector, so we know that, and then it was supposed to have a length of up to between 2 and 5, and each time, this was actually not specified in the data specification here, but I did assume that, flip a coin, with 50% chance we add a string, and with 50% chance we add a number, which is either an integer between 0 and 100, or a floating point value between 0.0 then and up to 100.0. And the floating resolution you can put in this range like this, which is like how small steps are allowed to be taken here in this range. So and then we push this to our vector, we update the vector, and then we save this value, the vector, for this key in our dictionary and return the dictionary, right? So, okay, a little bit convoluted, but also what you were requesting here was a bit convoluted. So you can see that when we run this piece of code, we get some dictionary here. It has strings of a certain length, random strings as keys, and it maps to a vector of, either integers here and a few strings, or there can sometimes be floating point numbers in here. So you can see, what did we have? Let's do instead maximum 5 entries, shorter strings, so the maximum string length is 4, and then increase the float resolution instead. So we do 0.001. So if we run this, you see we get more digits in the floating point numbers here, right? So you can play with a custom generator like this by writing custom code that will generate a random data of the format that you want. So this is very powerful. It can adapt to your specific criteria, but of course you need to then write the code that encodes these criteria. So there are different approaches here, but in general, this is the type of thinking that goes into random testing. Thank you.